So in this video, I'll be continuing on the third part of my water series. I'm gonna talk about the solvent property in this video. In my previous video, I went over the adhesion and cohesion properties of water, and before that, I talked about hydrogen bonding in water. And I recommend you check out especially this hydrogen bonding video because they explained in a clear manner how water does hydrogen bonding, and hydrogen bonding is so important in all of its properties, including cohesion and adhesion. So if you can watch that and understand it, then you won't have to memorize any of these um, uh, properties that water has, any of these four. So, but for today, I'm covering the solvent property. So I'll try my best to explain this well. So I don't know if you've ever heard this, but water is sometimes known as a universal solvent. So I'm going to try and explain what this means, why water is a universal solvent. But before that, I need to use this analogy. So there are four individuals here. How would you think if all of these four individuals went to a party? Who do you think would end up talking to each other, and who would not? So I'll give you a second to think about that. Okay, but what I think is the two sports people should hang out, right? I don't know what you think, but I think that definitely could happen. Wait one sec. Yeah, I think the two sports people would hang out. The bodybuilder and the football player, right? Or the soccer player. Because they have something in common, right? And that's sports. Even if it's not the same sport, they might prefer talking to each other than to this guy talking to a scientist or the nerdy guy. Because they have more in common, right? So they would rather hang out, I would say. And this guy would, yeah, he would rather hang out with the more educated, whoever this is, a student or whatever. Because they might have more to talk about than the businessman with the football player, right? This is just a guess. This might not actually be true, but this is what I think would happen. Now that we've matched these up based on something they have in common, this actually kind of relates to what water does in terms of its solvent property. Water, as we discussed in my first video on hydrogen bonding, water is polar, right? Because it has the slight positive charge on the hydrogen and the slight negative charge on the oxygen, which makes it overall polar. Now, all molecules or things on Earth are either polar or non-polar. Okay? So, water is polar, like I just said, along with a few other things, which I want to get to. So, sugars are polar. Let me move these guys up a bit. So, sugars are polar. Amino acids are also polar. And you'll see what I'm getting here. Amino acids are also polar. Yeah, and again, water. Here's water. Now, what things are non-polar? What things are not polar like water? Lipids, proteins, cholesterol, there's many things. And there's obviously, these are not the only three things, there are many more things. I'm just showing some important ones. So just like we match these guys up, we can match these guys up and all of these random guys in terms of their polarity. In science, things that are polar will come together, and things that are non-polar will come together. And what this means is polar things will dissolve other polar things. So if you put a polar thing, say a sugar, into water, it will dissolve, which means after a while of stirring it, you won't see the sugar anymore because it would have dissolved. They like to hang out. But if you try to put a non-polar thing into a polar thing, like water, they will not dissolve. They will not be suitable for hanging out in the analogy. So if I put lipid into water, they will not dissolve. And you'll see that when you throw oil into water or fat into water, you'll notice that the oil just floats to the top. And no matter how much you stir, it won't dissolve. And that's what I mean here. So polar things like polar things. So polar things will hang out and they will dissolve each other. Non-polar things will not hang out with polar things. They will stay in their own little group. Okay? So if you can remember this analogy, you'll remember this. Polar things like polar things, non-polar things like non-polar things. Now I'll try and explain with a diagram what this really looks like, just so you can really understand. But if you can just remember polar things dissolve in polar things and non-polar things dissolve in non-polar things, it should make sense. And the reason why this is even relevant to a water property is because most things on Earth are polar. Most important things on Earth are polar, which means water can dissolve most important things. There are less things that are non-polar, less things that are not as important. So that's why water is cool, because it can dissolve many of the most important things on Earth. It's due to most things being polar, like water itself. So if you are to look at the diagram, I want to show you. So say you have a cup of water. Okay, these are water molecules. By the way, if you check my first video, you'll know, because I used a similar diagram. So yeah, that's a cup of water. You pretend there's hydrogen bonding and everything in between, and the water molecules are polar. I didn't label it, but it is, so it's polar. Now say you want to add salt to it. You just want to throw in some salt. Everyone does that. It's like sugar. You can just try and throw some salt in and see what happens if you stir it. Because the ocean is salty, right? And that's because salt is dissolved in it. So what do you think will actually happen if you try and dissolve this salt in there? Is salt polar or non-polar? Because we know polar things dissolve polar things. So we know water is polar. Is this polar? Yes, salt is polar. And you can see, because in this diagram, there's a positive and a negative. And if there's two extremes, a positive at one extreme and a negative at the other extreme, it means it's polar. So if you throw salt in here, oh yeah, this is just the science way of writing it, NaCl. If you throw it in there, it will bond and it will mix, so it will dissolve. So after a while of stirring, you won't see it anymore. And the reason is because this is how it looks like. You notice that the water molecules arrange itself around, it breaks these two apart, and that's what you call dissolving, when you break the molecules apart and you dissolve them separately. So the water molecules arrange themselves around these Na and Cl. For example, the Na is the orange one, and it's positive. It is positively charged, and the oxygen, the black one, is negatively charged. So you can notice that the water arranges itself so that all the negative-facing oxygens bond with the positive Na, or the positive sodium. And then the Cl that is negative bonds with all the positive-facing hydrogens. So this way you can see it's dissolved. It doesn't stay at the surface, it actually mixes in with the water. And that's why you can't see it after a while, because it's all split up and dissolved. What do you call something that wants to be dissolved in water, like NaCl? So most polar things, all polar things, like sugars, amino acids, salt, they all want to dissolve in water. And this, the scientific name for this is hydrophilic. It means that it wants to dissolve in water. And you can split this word up into two. So hydro and philic. Hydro literally means water. Like, yeah, you can think of hydrated. Hydro means water. Hydrated means if you have enough water. Dehydrated, not enough water. But just think, hydro means water. Philic means loving. So if you put those together, water loving. So all polar things, all polar substances are hydrophilic, which means they love water. They would love to go in there and dissolve. Okay? Now let's see what it looks like if you try and throw something that is non-polar into water. So you bring a non-polar and a polar thing together. Obviously we know that's not good. They're not going to dissolve. Because polar things stick together, non-polar things stick together. But I'll show you a diagram anyways. So again, we have the cup. Okay, we bring a lipid. An example of a lipid, by the way, if you watch my first video, is methane. Methane is a carbon attached to 4 hydrogens. It is non-polar. You can see there's no positive or negative ends. It's just like that. And that's why it can't do hydrogen bonding. And yeah, so it's non-polar overall. There's no negative, there's no positive and negative ends to it. Okay? So just remember that. This is just an example. Methane. It's one you should know for the IB because it's like the exact opposite of water. It has the exact opposite properties of water just because it doesn't have hydrogen bonding and it's non-polar. So it's good to know this one in case they bring it up in the test. But yeah, so you try and dissolve it. Here's the arrow. But what you're going to notice, let's pretend the lipid is this red molecule, okay? So you'll notice that it doesn't want to mix with the water. It just stays on top. And the reason is because there's no positive end that wants to bind with the oxygens, and there's no negative end that wants to bind with the hydrogens. It's neutral. It's non-polar. So it doesn't comfortably go inside and mix because there's no positive and negatives that can attract. So it just stays at the top. And that's why you notice the fat always floats on top, because that's literally what's happening. It's because it's non-polar that it can't mix. And like we had the word hydrophilic for things that want to dissolve in water, all polar things, we have a word for things that don't want to dissolve in water, and that's hydrophobic. All non-polar things are hydrophobic. That means, literally, if you split it up, hydro, again, means water. Phobic, you can think of that as like normal people have a phobia. You can have a phobia of height, and phobia literally means fear. So you can say water fear. It's literally afraid of water. So it would not want to go in there. It would rather stay on top, as far away as possible. Okay? So in summary, water is polar, so it can dissolve all polar things. It will not dissolve non-polar things. But luckily, most things that are important on Earth is polar. So therefore, water is a really good solvent because it can dissolve almost all things, because almost all things are polar. Now, what do you do for things that are non-polar? Because you saw here my list, there are some things that are non-polar, but they seem important, like oxygen, that definitely, and carbon dioxide, that definitely seem important. Some proteins, you do need these, right? So how does your body, if they can't dissolve in your blood, because your blood, remember, it is mostly water. So if your blood is mostly water, how are these things going to dissolve in your blood to be transported to the rest of your body? Because they can't. They're non-polar. So they won't dissolve in your blood to be transported somewhere else. So the question is, what does your body do to move these things to the parts of the body that need it? So it's actually a really interesting concept. And they use something called lipoproteins. So lipoproteins literally are like a little thing. It's like you can think it's like a little ball of something, a little ball that puts all of these things in the middle and moves it throughout the blood. So that it doesn't have to be, so that all these non-polar things, all of these things are non-polar. So that all of these non-polar things doesn't have to come into contact with the blood. So this is your blood. Let's pretend this is a vein or something. So this little ball, all these red balls around, they protect these things from the blood. But I'll explain more detail because that's pretty much what they do. But if I explain the real mechanism, it might become more clear why it does that, how it does that even. So how it does that is, let's first label the diagram so it can be clear. Okay, so there's three key parts to this diagram. There's this thing, the red thing with like little string-like things on it. So this is the most important part of this lipoproteins. And you can think of lipoprotein because lipid sounds like lipo, and lipids are one of the things that are insoluble, that are nonpolar. So it's a protein that carries things like lipids around your blood. So yeah, this thing is the most important thing, and it's called a phospholipid. In one of their, this is something you should learn in the IB, because it's part of the membrane structure that you learn in chapter 1. So a phospholipid is very, very important in this structure because it's amphipathic. And amphipathic is a good word to remember because it's one of the key words. It literally means both water-loving and water-hating at the same time. You might be like, wow, that's weird. How can you like water and hate water at the same time? Because this structure actually works like that. So the red part of the phospholipid loves water. That's why it's facing outwards to the blood, because it would like to come into contact with the blood. But then the tail thing behind hates water, so it'd rather face inwards. And that's really good because if it faces inwards, it means there's no water in here, there's no blood in here, because this red part is causing all the blood to be outside. It's facing outwards. So that this part in here has no water. That's why the water-hating, the hydrophobic tails, these hydrophobic strings, are comfortable because they're not into contact with any blood. So this structure is really good because it can form this kind of arrangement that allows for other polar things to come inside and also be comfortable. So this, by the way, here is cholesterol, and this is not also cholesterol. It's like fats. I forgot to rename it, but you can just think lipids because they're nonpolar. So this sort of thing right here, this protein here, would bring in all of these nonpolar things. And now that because of this amphipathic phospholipid layer, all of these nonpolar things are comfortable inside here, and they can easily be transported inside this lipoprotein along the blood until a body part that it needs. But most other things that are polar, like sugars, like we saw, sugars, NaCl, salt, whatever, all of those things can just go straight into the blood, dissolve, and be carried around. It's just these non-polar things that your body still needs but won't dissolve in your blood that needs these lipoproteins in order to transport them for you. Okay, but that's it for this video. I covered now solvent property of water. All of this stuff I'm explaining is the absolute most detail you need to know to get a 7 in the IB. Everything I covered, there should be no more. This is all the IB is allowed to ask. So don't, if you watch this video, you should be comfortable knowing that if you know all of this stuff and you understood this video, that's all you need to know on this specific topic. So I hope you understood it, and stay tuned for my next video, which will be on thermal property of water. And make sure to check out hydrogen bonding if you haven't.